Hello, everybody. I hope you can hear me well and everything is visible. And with that, let's start. So, welcome to our workshop. The topic, of course, is the basic of Rust. But this is more of an introduction to the Rust as a programming language, as a pivot on the frontier of blockchain technology. And my name is David, or David, if you prefer the Western variant, and this is my colleague Pavel. And today we're going to try to walk you through first the basics of Rust, like from the simpler 101, and then gradually build up to more advanced concepts. So probably we hope everybody could take home something from that talk. Our workshop is roughly separated in two parts. The first one is the presentational part, where we're going to talk more generally about Rust, its concepts, its ideas, discuss some of those, and philosophize a bit. And then we're going to go to the more practical, hands-on part, where we're going to accent on demonstrations and get a feeling about Rust in code. So the whole duration of the workshop is going to be about 2 hours, with a small 10-minute pause somewhere around the first hour mark. And if you have any questions or something was unclear, just feel free to interrupt us, ask your questions, and we're going to be following for questions in the chat. So with those details out of the way, let's start. And we are, of course, going to start with the most basic and important question. What is Rust even? Now, we were aware that the level of familiarity with Rust is going to vary among the audience. Some of you might have only heard about it, some of you might have dabbled here and there in Rust, and some of you might already be churning production code in Rust, right? But no matter we rely on that spectrum, we are sure of one thing. You have at least once in your career found yourself in a similar position to our guy Homer here, you know? So today, friends, we're going to be that guy behind that door. We're going to be preaching to you about Rust, but we hope to make this more constructive so you can actually extract some value from this. So with that, let's start seriously with the first part, where we do the lots of buzzwords, okay? So what is Rust, seriously now? First off, Rust is a general purpose programming language. Now you have most probably heard about that a lot, but actually what does that mean? Like, I've been wondering myself, that's not very determined, very defined. Well, for me, to put it simply, general purpose means simply that you can do pretty much anything you want with the language, okay? We can safely say that Rust is a systems programming language, meaning you can actually do really low-level stuff, like embedded software, right? Embedded software, okay? And you have most probably already heard about parts of the Linux kernel being rewritten in Rust, okay? So it's really great about such purposes. Now, you can also use Rust for more classical use cases, like implementing a server, okay? And you can even use Rust to write your front end, going through WebAssembly, okay? Which is a keyword you are going to be hearing a lot in the blockchain domain. But yeah, we'll leave that for later talks. But that's like an actually relevant current thing, like a lot of work done with WebAssembly. And there are, of course, also higher level applications of Rust. So there are, for example, a couple of game engines written in Rust, which you can use. So yeah, basically you can do anything with it. It's not a domain-specific language, for that matter, not like SQL for databases or R for statistics. Now, next up, Rust is a compiled language, which is a simple notion. It means basically that you do not have an interpreter that you need to run in the background to interpret your code. Okay, so it's not like a scripting language, which is the term. You also don't need a virtual machine. Like Rust does not transpile to some kind of intermediate bytecode like Java does, for example. So it compiles to native executables, runs on bare metal. So yeah, that's that. It's a compiled language which talks to your CPU directly. And last but not least, and this is where it gets really interesting, Rust is a multi-paradigm language. Now, that part of learning a language is always really exciting because those are not precisely defined, okay? Paradigms are those vague notions that we like to put as labels on languages in order to gain a general understanding of the language. And this here is our best effort to kind of extract the three most essential, in our opinion, paradigms that Rust supports. Okay? So we are going to start from left to right, and we had to do our due diligence to say that Rust is firstly an imperative language. And what does that mean? I hope most of you have a notion of what an imperative language is, but to put it simply, what is that thingy here? Okay, never mind. Okay, that simply means that as you write your code, line by line, okay, those lines you write are sequentially translated into instructions to mutate into your business logic, right? To mutate the state of your program. Instructions are executed sequentially. That's basically what imperative means. Now, the more interesting second one is that we can safely say that Rust is a functional language. Rust has borrowed a lot of ideas from functional programming, like from that part of the programming world. First, the idea of immutability. So you have your data, like everything is a constant, okay? Data being constant. And another really crucial thing is that functions in Rust are first-class citizens, which basically means that a function has a type, and you can assign it to a variable, and you can pass them around freely like any other variables. So that's really cool. And it also naturally alludes to the next bullet point here, which are higher order functions, also a very key idea from functional programming. Now, a higher order function is simply a function that either accepts another function as an argument or produces and returns a function as its return value. Okay, and those are very often lambdas, also known as anonymous functions. Or closures, yeah, from other languages. Exactly. And the last bullet point here we decided to list is a very key one, algebraic data types, which might sound a bit scary if you're not familiar with that terminology yet, but don't worry, we are going to go see this in our practical part of this workshop, so in our demonstrations. We'll get a feeling about what functional means. Now, the last paradigm, and probably the most famous one and the most exciting one for most of the programmers, is object-oriented. Now, we have put 3 dots here, and that's not random, because this is a rather controversial statement, in our opinion, to say that Rust is object-oriented. So we can take that with a little grain of salt, right? So we can kind of think of it about that. Now, we can say that Rust is object-oriented because it does indeed support the notions, those concepts of object-oriented programming, like encapsulation, the idea of hiding away private details of your modules and classes, whatever that means, in your language. So you can differentiate between private and public. You can encapsulate things. You can also achieve abstractions, which actually for me just means hiding the complexity of things behind a simpler interface. Like that can be a function which you implement. So that's the abstraction. Or we can talk about swapping implementations behind a generic interface. You can do those things. You can achieve abstractions in Rust. Now, Rust does also support a similar notion to methods, in the sense that you can define your data, and then you can define behavior on that data. Okay, so we can talk about methods in Rust, and we can also achieve polymorphism, which could be a bit complex as an object-oriented notion, but simply that's the notion of being able to look at things from different perspectives, like having the same thing and looking at it in its different forms, like you're interested. Yeah.
Or look at many different things using the same lens to look at them as if they were the same object, having a small subset of common functionality, like an interface.
Yeah. So those object-oriented buzzwords, we can have those in Rust, okay? But be wary. You probably do not have them in Rust in the way you imagine, okay? We do not have them in the traditional sense. Like, first and foremost, Rust does not support inheritance, okay, from classes. We don't even have classes and interfaces in the traditional way, like in Java or C#, okay? So be wary that you might feel like that's not entirely true, and Rust is not entirely object-oriented, but it actually, we could make the case that it is. Yes. So, by the way, that little orange thingy here, that crab-looking creature above, that we showed you, wondering about whether Rust is object-oriented, that's no random creature. It actually does have a name. And its name is Ferris. And that is Rust's official mascot. It's a crustacean kind of creature. And he's waving hello to you. Yeah, so you can wave back because we're going to see him a lot through this workshop. And yeah, generally, if you work with Rust in the Rust fields, Ferris is, I think, the mascot of Rust. Yeah, so with those common things, generic things out of the way, let's now proceed to more buzzwords for you. Okay, so we are going to take a brief look at Rust's core features in a flat list, like we thought appropriate. And first and foremost, of course, relating to our meme at the beginning, we must start with the perhaps most prominent feature of Rust, which is its fabled memory safety, right? Okay, so Rust is very memory safe, but what does that mean? Now, usually, when we talk about memory management and memory safety, languages go ways, generally, that is. And the first one is memory management being very manual. And we are familiar with that most predominantly from the lower level programming language. And let's be fair and blunt, that's mostly C, which has dominated this domain for a good couple of decades, or a lot of decades. No, actually. So what does it mean is basically that the language, C or C++ in that case, provides you with the basic functionality to do whatever you want with memory. And it just raises its hands and says, okay, you have the entire power, do what you will, but you as a developer must follow what memory you allocate, how often, where you free it, and who is able to mess around with it, okay? And you have to explicitly control that and think about those things.
Yeah. And if you mess up, you pay the price.
Exactly. Yeah, as we famously know with C, it's really easy to shoot yourself in the foot when you do that, okay? Manual memory management. And with C++, admittedly, as Bjarne Strastrup has famously said himself, it's a tad bit harder, but when it happens, C++ like hands you the shotgun to blow your entire leg off, right? And then some of the floor underneath. So yeah, funny memes, we're having a good laugh, but it's that's a bad thing. We don't like when it happens because it's very fatal most of the times. So a solution to that problem is our second approach here, listed as a bullet point, which is this notion of garbage collections. Now, I assume some of you might be familiar with that, and probably will be familiar with that, what garbage collection is, but it basically means that you don't have to think about memory as a developer anymore, so that's good. We don't have to do that ourselves, but you have to have this garbage collection process, the garbage collector, running alongside your application, your actual business logic, and taking up from your resources, like runtime resources, to do all that messy work for you, okay? So it comes at a runtime overhead price. And there are scenarios where that's a deal breaker, okay? Like where performance matters. And
or for example, Mako software and hardware, for example, peacemakers, it's not a good idea to put Java on them because the GC cycles could interrupt and mess with the timers and all.
Exactly. So yeah, now we have included a little case study exactly about that. Garbage collection is a problem. And I'm going to tell you a story, the story of how Discord migrated from Go to Rust, okay? So this relates to their read states service, which is basically a microservice they have with the sole purpose of keeping track of which channels you have read. Okay, channels and messages and mentions, all of that thing you are used to seeing in Discord, that's the service that handles that. It's very read-write intensive, so we're talking about hundreds of thousands of cache updates per second, and then tens of thousands of database writes when cache is evicted. So really read-write heavy service, and it was initially written in Go. Okay, but there was that one very nasty issue that every once in a while it experienced really heavy CPU usage and latency spikes, which were then slowing down the application tremendously and propagating to the end user. So yeah, that sucked a bit for the crispy, clean experience of this code. So they had to dig to find that, what was causing that. And the culprit was actually Go's garbage collection cycle. Okay, because it turned out that Go would forcefully garbage collect at most every 2 minutes. That should be seconds, perhaps. Sorry, yeah. Yeah, so that was a deal breaker, really hard to modify, and they went on the search for solutions, and they came across Rust, because Rust does not have a garbage collector, like at all. This notion is abolished. So they figured it was worth a try, like you could try it, might be better. And even with the basic optimizations, like a little effort, relatively little effort, they were able to solve that issue, and the Rust version was even able to outperform the really precisely hand-tuned version of Go. And then, after a bit of more profiling and performance optimizations, it was able to actually outperform it in every metric. Like, yeah, latency, CPU, and memory usage, all those things we have listed here. So yeah, that's actually a really nice case study of why it's useful and important to know your tooling and those really crucial, I would say, features of languages, right? And by the way, this story is a summary of their blog post, which we have linked here under, so you can go read it. I would recommend.
Yeah, we'll post the slides later.
Exactly. So, as we have seen here, Rust does neither of those two things, okay? You don't manage memory manually, but it also doesn't have a garbage collector. What it does, we will see in more detail in our demonstrational part, okay? We will explore exactly that part of Rust, how it handles memory.
But in short, it takes the best of both worlds and none of the worst.
Exactly. Okay, so next up, really crucial, performance. Now that's the part when you hear people say that Rust is blazingly fast. Yeah, it's basically because it compiles to native executables, as we have already said. So we get that benefit of C and C++ as languages. So we do compile, it runs on bare metal, right? And Rust also comes with built-in tooling for cross-compiling, which is a big bonus depending on your needs. Okay, so you do have built-in support for many platforms, and of course under those are Windows, Linux, and macOS. And we have put here without too much hassle, because I was about to initially say that you could do that seamlessly, but yeah, that's an overshoot. It's never an easy thing. But the build system has thought of that, so that's really cool to know. Right? You want to add something?
Yeah, no, cool. That's it.
Then, next up, also a very spoken about feature of Rust is its prominent type safety. Now, there's a lot to unpack here, but in more technical terms, type safety means those two things. Rust is a statically typed language, which basically means that everything has a type known at compile time. And that type is, in a lot of cases, inferred by Rust. Okay, so Rust does support the notion of type inference. And it is also a strongly typed language, which is a bit more undefined as a term. But for us, that basically means that typecasts are explicit. So you don't have anything like truthiness and faultiness, like you have probably seen in other languages. And also, yeah, no implicit type conversions, okay? The cool thing about that is that you can rely on the compiler to really handhold you, as we have put it here, while doing that. Now, those are the technical terms of that, but what's the really cool thing about Rust's type safety is it's really developed type system, okay? Which gives you really a lot of power while preserving your safety and comfort. And we're going to showcase that later, so what we mean by that. But just stick with that for now. Really advanced type system, really cool, really powerful. That's the key takeaway here. And next up, this term, fearless concurrency, we have borrowed from the Rust book. Was that, I think?
Yeah.
From the book. Yeah. Okay, it's not a thing we came up with. That's something that Rust brags about itself. So of course, we must say Rust supports the asynchronous programming through to via the usual async await syntax we're all accustomed with. Yeah. But the fearless part, what's funny about Rust, that it has put emphasis on preventing a lot of the common pitfalls when doing asynchronous programming. So things like data races, deadlocks, I love those problems. You have support from the language to avoid those, thanks namely to that advanced type system and the memory management mechanisms. Okay, so there's a lot of effort being put into that. Yeah, next slide. We have formally named those other features as being not so buzzwordy. But yeah, very nice about the developer experience with Rust is that you have a lot of neat, helpful compiler error messages, which is honestly like nowhere else. We have done our fair share of programming languages, I would say, and yeah, those are really just nice, clear, informative, nice to work with.
And we'll see them shortly in our first demos.
Exactly. We'll be seeing a lot of those, so brace yourselves. Now, Rust is also very flexible, which basically means what we meant by that keyword was that, as you might have gathered already, there are a lot of new concepts, restrictions the language imposes on you, but you can always opt in to willfully tell the compiler, just let go for a second, okay? I know what I'm doing, and you can opt out of all of those restrictions. And this is oftentimes useful when you want to do like really basically write C in Rust, okay? You can do that, but it's still better, we must say.
Unsafe Rust is still safer than normal C.
Exactly. But yeah. So that third thing here we have put feature is a rather niche one, but for the lower level geeks amongst you, it's really crucial to mention that Rust has a C FFI, which means a foreign function interface, which basically means that you can write your functions in Rust, and then use them from other languages that can talk C, which is mostly C, I would guess, like C++ or any other language that actually has an implementation of a C foreign function interface.
Even Java has one.
Even Java has one. So a thing that happens a lot in blockchain is you have a native binary written in Rust, which is cool, does its work, but you want to use it from a Go implementation or like Java implementation, yeah? You can do that fairly easily. Right? It's never that easy, but it's fairly easily. Rust has support for that. And last but not least, a bit on the non-technical community side of talking about Rust is that it's a really live and thriving technology. It has gathered a significant adoption throughout the years up until now, and it has been ranking as one of the most, if not the most loved programming language in industry surveys and community surveys. Like you've probably heard that Stack Overflow Rust tops the list, I think, for the past
6 years.
6 years that was.
Yep.
Yeah. So people love it, and there's a lot being developed currently in Rust. So that was the storm of buzzwords. I hope you could take away something from that. We will get a more practical feeling about that, to say once again, in a while. Now, before we jump into the demos, we must talk about cargo, because no language is good without its build system and package manager. And cargo takes the role of both for Rust. So it is a package manager and a build system. It can manage your dependencies, of course, and by manage we mean it can define them, like resolve versions and find them in the corresponding source registry, yeah, and it can then download and compile them for you. It can also then compile your project and run it, which is test it, of course, run tests, of course, which makes it a build system, and you can also publish your work then to a registry of your choice. That's mostly Crates.io, which we have linked here. So yeah, it does all of that for you. And a really fun thing, important thing we should mention here is that packages or external libraries in Rust are called crates. And you might start noticing that cargo, crates, and there's a lot of ship-related lingo around Rust for some reason. But it's just like Python and snakes, right?
Yeah.
There's just this notion of it. To put it simply, in other words, the relationship between Rust and cargo is the same one like JavaScript and NPM, like Java to Maven, or PHP and Composer, and the list goes on and on and on. I hope you find yourself familiar with some of those. And we can see that's a relationship of a lot of love, because languages love their package managers, right?
Yep.
Exactly. Cool. So that was the most dense content thus far. I hope it was not too heavy and too much talking. And just before we go really this time into the demonstrations, just to relax a bit with a fun fact. Now, ever since I first heard about Rust, this question really stuck with me, like in the back of my head. Why would you name your programming language Rust? Right? That's a weird name for a programming language. And I did a little searching out of curiosity, of course. So a little backstory. Rust was initially created by a guy named Graydon Hoare at Mozilla Research. Started in 2006, and it got officially funded in 2009. So it's not that new, but still relatively new in terms of programming languages. And all the things I'm going to list here are actually speculations on his part. So there are no concrete answers to that question. But first and foremost, Rust has been said to be named after a particularly robust type of fungi that is quote unquote over-engineered for survival. So it's a fungus that is really parallel and distributed, like really efficient in nature, can survive dire conditions, and they also look like that, might you see. And that is a leaf of a plant. That is no piece of metal. So also they look like rusts, right? That's why they were called rusts. And combine that with the fact that Graydon was a bit of a biology geek too, and yeah, that adds up. Rust also sounds a bit metallic, having to do with the notion that it runs on bare metal, like big heavy machinery, metal machinery. Cool. And a little bit of wordplay at last. Graydon has also mentioned that it's a nice subsequence of robust and also trust, because you could trust it, but also frustration, because, yeah, it could be difficult at times. But not to scare you off, we will see what we're talking about. You can find the source of all of that information in the Reddit thread we have linked. So, yeah, I hope that answers it for you. And with that, it's time to start with the practical part, the demo time. So, a quick plan overview of what we're going to cover. First, we're going to start, as I said, with the really, really basic beginner 101 stuff, like Hello World, because of course to start with that, with Hello World, and then explore the basic syntax, primitive types, basic functionalities, how functions are written, and so on. Then we're going to showcase the memory safety mechanisms, because we think that's really important.
Then we'll have a 10-minute break.
Of course, somewhere about that time mark, we'll have a 10-minute break. Then we're going to build up a little more complexity, like actually doing more sensible stuff, defining our own data types, defining behavior on them, talk a bit more about this OOP part we mentioned. And then the third point here, we are going to showcase the power of the type system with a little case study on the foreground of error handling. That's a common programming problem. So yeah, with that being said, I am handing over the initiative to my colleague Pavel to begin with the demos.
So now let us transition over to the more technical part of the workshop, the demos. So firstly, we'll look at how we use Cargo to create projects. And inside one of those projects, we'll look at, as my colleague David said, some basic syntax, types, and functions. So let us neatly transition to my other screen and show you. So here is a terminal. Don't get scared. With low-level languages like Rust, you have to get accustomed to it. So how we use Cargo? It's a CLI tool invoked with Cargo and has a command new, which creates new projects. We can give it a name, let's say workshop. Okay, and this creates a new folder called workshop, as you can see here. And inside of it, you can see we have two files, Cargo Tomo, which we'll talk about a bit later, which is like your package.json, the metadata for the project. and a source directory with one source file. So let's open our editor of choice, and let's see how this file looks. So here we can see we have a function which is defined by the keyword fn, a really short one. You can see because Rust is a functional language, we use functions really often, so they decided to shorten the keywords used for creating functions to just fn. We can see a name here, a classic parameter list, and a body. As you can see, the syntax of Rust is quite C-like. So we have bodies using braces.
Yeah,
working curly braces, expressions sent with a semicolon, and the like. So here we can see actually a macro call, but let's call it a function call for now, to print line, which prints the string hello world. And I believe I can run this code, and here you can see we have the output of the compiler and then the output of the binary itself. So to not waste our time, I will not live code all of the basics and instead switch to a predefined let me see, demo project, yes, which resides here, which is the same structure, but we have a few more files here. So again, on the basic syntax, put here, yes. So as we saw just now, here is how we define a function, and as David said earlier, we have publicity, is that the word?
Yeah, we can pub modifier.
Yeah, we can make things public, which means that when someone consumes this file / module, whatever that means, they'll be able to see this. Think of it as export in other languages. So here we can see a main function. The variable declaration syntax can look similar to JavaScript or more like TypeScript. So we have the keyword let, an identifier for the variable, an optional type annotation, which can be really often inferred, equals, and some expression. So here I'm showing what a Boolean expression might look like. We have the usual and or operators, and true and false as keywords. A bit above, I've defined a small function, which I'll now show. This is a function that, unlike main and unlike this one, returns something. So we type the return type after the parameters. Some languages decide not to have a function keyword at all and just use the return type instead. But Rust chooses to do it postfix. So we have an arrow syntax and a type. We'll now say what that type is. So here we call the function and assign to a variable. So what is this magically looking i32 type? So this is an integer. And unlike C or most of the C-like languages, integers here have a really precise syntax that describes them beautifully. So we don't have a byte short, int, double, float, wonk, double, wonk, wonk, double, float, and a backflip. Instead, we just designate a letter to know whether or not the number should allow having negative numbers inside of it, or not. So I stands for integer, U stands for unsigned integer. And then we just have the number of bits we'd like to have in the number itself. So for example, U8 would be an unsigned integer, which is constrained by 8.
Some technical issues we're experiencing.
I think we are back. Okay. So where were we? Yes. So we have floats, and instead of saying floats and double, we just have F for float and 32 because that is the normal size of a float type, single precision floating point number. And instead of double, we just have the same F but double the bits, 64. There's also a bit more extended float types that have 80 or 1 28 bits, but we won't talk about those. So as we saw above, we call functions using the name of the function, then parentheses with the arguments inside. And example for this would be the function that we defined in the start of the file, print hello, which takes a number argument. We called it num with the type of i32. And you can see the syntax for arguments is the same as for variables, name, colon, space, and a type. And what does this function do? It prints something. It prints hello world, my favorite number is. And here we can see how this print function is actually a printf in disguise, because we can put holes for arguments here and then a letters replacement. And because the type system is super generic and smart, we do not need to specify the exact percentage D or F or whatever C does to say what we want to do here. So let's look at this getNum function for a bit. You will see now that first, we don't have a return keyword for some reason. And second, there is an if here that looks like it has something to do with numbers. So Rust has a return keyword. Nobody can stop me from writing return free. There is a return statement, but most commonly, because Rust operates on immutable data and doesn't do much, many side effects most of the time, when we create small functions like this, we like to use the feature that Rust gives us called implicit return. So if we have an expression at the end of a function and don't put a semicolon after it, it is interpreted as an implicit return. But now, where is the expression here? Well, it turns out, instead of having a special syntax for ternary operators like JavaScript and C do, the
question mark column combo.
Something true, false, like this. Instead of having this, we just use the if. And here we can see how an if statement looks. Spoiler. We have an if, no parentheses, a Boolean condition, a body, an optional else, and the else body. And here, just like I've said about the implicit return, we can just leave a 5 here and a 6 here in these bodies. And this actually turns this if statement into an if expression, which means that if we want to, I can do let Higgs be this and put a semicolon, and suddenly Higgs is now an integer. By default, number literals are i32, as you see, which is almost the same as int in other languages. And if you want to, we can now either do a return Higgs explicitly or just say Higgs. And Rust will now say, but wait, you see, this is not an error, it's not red, but it will say, look at what you're doing. You're doing a let, and then you're returning the thing immediately after. And you don't need to do that. So there's a lot of small lints integrated into the compiler, which hint you, and if I remember correctly, even can be automated automatically.
Yeah. So it makes for a really nice experience while developing.
Yep. So here we can see automatically. Another part of the syntax for cycles. So this function that shows numbers, we haven't called it yet. It's more on the bottom. We have 4 cycles in Rust. And here we've decided to show how you can iterate on ranges, which is another feature of Rust. We won't delve into much. Yeah. But you can do cycles over ranges of numbers, for example. You can also do it on incoming TCP requests or lines from the day in, or on vectors, let's say. So you can iterate on each element of many things. We will look at what that means later. So more syntax. We have while loops, which look like this, and follow the style guide from the if, we don't do parentheses like ever for some reason. Those developers have decided that it's cleaner.
Yeah.
Okay.
Exactly.
Other things. So here we can create, just for the demonstration purposes, a small while loop that does nothing. And instead of doing while true to create infinite loops, Rust actually has a loop special keyword, which is almost the same as while true, but it's actually an expression of itself, because a while loop may just exit immediately, but our infinite loop, which has no condition and is always infinite, may either break or just run infinitely. So we can be sure that if we somehow get out of it, we have breaked out of it, not that any condition is stopped. So knowing that to get out of the loop, you always have to break, we can actually attach some more functionality to the break keyword and let it break with a value. And here we can see not only the if, the while true or the loop is also an expression, which you can use this for like getting valid user input. Let's say you print line, please enter a number, user enters some string, you check if this string is a number, if it's not, you just loop, and if, yes?
Yeah, I just wanted to say that this particularly might seem a bit strange at first, depending on your background and what languages you come from, but it's really cool once you get used to it, like having these blocks returning stuff. Okay, that's really cool.
Yeah, it composes really well. So yeah, if you have a loop that should return a valid number from the user, it could loop inside and print to the user, please enter a number, please enter a number. And if it is actually a number, it could parse it and break out of the loop with it. Okay. And lastly, we call this show numbers functions. And so we can run the main and see what happens. And here we see our flow routes and prints. And finally, the big loop that cycles from 0 to 16 exclusively. Cool. So this was the introduction to the syntax. We'll now return briefly to the presentation, right?
Yes.
Okay. So,
Yeah, so just to breathe in and to separate those two pieces, that was the basic part, like really the easy stuff, I would say.
Yeah.
Now, we're going to explore in a bit more depth what Rust does do in order to manage your memory. And yeah, this slide is simply put here to hold all the buzzwords we're going to be tackling separately. First and foremost, Rust has a notion of ownership, which is basically the idea that every piece of data must have its clear and distinct owner. Okay, only one owner at a time, and it must be known. He must be known, the owner. Then we have the idea of mutability. Now, that is a question: which variables are actually variables? Which data is constant? Who can mutate your data and when? Okay, that's the key topic we gotta tackle. Then we have the really fun part about Rust, which is the borrowing system, and we have the famous borrow checker. So yeah, this is the notion of, okay, the data has a owner, but I am somebody else and want to do stuff with that data, so I'm going to borrow it. And how that actually happens, what are the rules that Rust imposes on us, we're going to delve into that. And there is the last, probably most complex, I would say, feature of Rust, which is this entire mechanism of lifetimes, which basically has to do with the scopes of your variables, and basically answers the question, how long does this data live, so to say. So yeah, things have scopes, and there are also rules about that, but this is the part we're not going to go that deep into. We're just going to tackle it a bit.
Yeah.
So yeah, with that out of the way, we're going to delve into the next demo.
So this is the first actual demo. Now we know what Rust looks like and how we can compare it to other languages in terms of syntax. Let's do something more real with it. So on to mutability. Now we'll dash through a couple of smaller examples, like smaller files, and showcase some unique ability of the type system here. So here is a small main function that in here we declare a variable x, and using the print line syntax that we saw before, we can print it. And what does this look like? X is 5, always good. Well, now I've changed my mind. I want X to be 9 now. So let's try to add 4 for it. Oops, Rust is now complaining that cannot mutate an immutable variable x. But where did I say that x is a constant? I told it to be just a let. And here's the fun part. In most languages, when you declare a variable, it is by default mutable or mutatable or whatever you want to call it. It means that you can change it. You can call functionality that modifies it. You can delete it. You can do whatever you want with it. And if you want something to be non-modifiable, or more commonly known as constant, you use a const keyword to signify that you want something to not be changed. In Rust, because having accidental modifications to your data where you meant it to be const but you forgot to are very common, Rust decides to flip the table around and have let the keyword for declaring variables, make them constant by default. And if you want to actually mutate something, you have to say it, change x to be mutable, which is done using the mute keyword, followed immediately after the let. And here you can see, if we tell x to be mutable, explicit, we can now do x plus 4 plus equals 4, and now x. If we save the file, x should be 9. Cool. And what happens if we make something mutable but actually don't use that mutability, which is the common pitfall of most languages? Well, Rust is actually, again, smart and sees there is a special link for that checks all your mutable variables, whether or not they're used or not. So here, Rust sees that this variable is actually not used, and we can remove this mutable decoration. Cool. So this is basically what we mean by mutability. Next, let's talk about copying data around. Let's say we have a simple number 5a, and make another number b equal to a. And everything is cool. We can take both of those numbers. Let's run this. Oops, a bit of spoiler. And yeah, didn't comment that out. So we can see we have both A and B. Everything is cool. But check your demos before showing. Okay, so if we try to do the same thing with a more complex data type, and here we see for the first time strings, which are, we'll talk about more later. This is a bit more, yeah, we'll see it in a minute. Okay, so this is how strings look like. The thing from inside is not really a string, it's a bit more simple thing than that. So if you want an owned type, like something that holds its own data and shouldn't be passed around easily, think of it as having a pointer inside or a handle to some data. If we try to do the same thing, like having s1 be string 1 and having s2 be the same, and then try to print them both, Rust starts give me a word. Complaining.
Yeah.
That we cannot use both of those because actually, by default, S1 takes, here's a buzzword, ownership. S2 takes ownership of S1. If you've heard from other languages like C++, for example, so-called move semantics, S1 is moved into S2, and we can forget about S1 as having ever existed, because all of its data is now inside S2, actually not copied, just changing its owner. It's not moving in data, there's no messing around. This just metadata who owns something in memory. So if we try to use them both, we get an error that S1 is actually moved, but also used after that. So if you want to actually have another copy of the string, we can use the built-in clone method. We'll see why we call it a method. And now everything suddenly works. So what clone does, it is the explicit way to tell Rust, okay, and I know that you want to save all the memory you can, but just here, just this once, make a copy of the memory. Not implicitly, explicitly. But why didn't we have to do that above? Well, for the primitive types of Rust, like numbers, actually, they are copied by default, let's say. So in cases where values would be moved, like here, they are actually copied by default because the copying is so cheap that we can just make it work like other languages. Anything to add?
Exactly.
So yeah, we've said that in the comments here. Everything is moved by default, but we can also clone it if we want. But
to make it explicit.
But yeah, because here the two keywords copy and clone. To clone something, it is an explicit operation that takes the data and by some miraculous algorithm creates a clone of it. And a copy means that the data is so trivial or simple that the compiler can implicitly just copy the bytes from one place to another without modifying anything.
Exactly.
So,
and
yeah.
if I can interject, you have the power to control that behavior. And what we're seeing here are actual implementations written in Rust for those primitive types.
Yeah.
Right? But you have full control of that behavior, saying when things can be copied and when you're okay with leaving them actually only clonable, so that you make your user have to type clone if he actually wants to clone it. Yeah. Which is really cool. So nothing is implicit.
When you create your own data, you can tell Rust whether or not you want this to be a feature or not. And here we can see, because the primitive types are copyable, which is the implicit clone, let's say, another warning by the compiler that it is not needed to clone because it is done auto-magically behind the scenes.
Exactly.
Cool. Next small demo is actually this one. Yes. Let's see if this is how it should be. It isn't. Okay, so when we work with data, excuse me for a moment. So let's say we have a function called string length that takes a string s and returns a usize, an unsigned integer that is just the length of the string, and we can use the len method of string here, which is built in.
Yeah.
Let's create a simple string like before. Let's try to take the length from it, and if we try to print them both, we get the same error as before, that something has moved. But here, instead of something getting moved directly by assigning it to another variable, it gets moved because we drop it into this bucket string length into this function, and the function takes ownership of that data and tells you, sorry, no, I take this string and I return you a number. You can't use the string anymore. So we get the same error as before. So what can we do here? And we see here Rust actually tells us the value is moved here, And actually, if the performance cost is acceptable, as we said, the cloning is something explicit that actually runs an algorithm to copy data. And if that algorithm, we deem it performant enough, we can do clone like before here. So we pass a clone of the string here, and we can still use our own to do the print. But this is a bit cumbersome. So what can we do better? First thing we can do is that instead of taking the string and just consuming it, we can actually give it back like this. This is the syntax for the so-called tuples, which allows us to return or like store many things in one. Yep.
Yeah, I would just note here that this might seem really odd and contrived to you at first.
Yeah.
Again, depending on your background, but this is a really common thing in functional languages. Like if you've ever done a bit of Haskell or some kind of Lisp, right?
Yeah.
We do that a lot. Like this notion of returning your values here and there if you need them. Because yeah, in functional languages, everything is a constant.
So
just a side note.
Yeah, you can think of it like anonymous struct with two fields, the first and the second one.
Yeah.
And their names are actually 0 and 1. If you have a value of this type, we can take out both of the things. So let us modify our code a bit here. So this is no longer a len. We can call this the pair. And then say that the S is the second element of the pair. But because it's indexed by 0, dot 1 will give us the string field, and dot 0 will give us the first field. And everything works again. And let's remove the clone to prove that it actually works. Yeah. So we pass the string into the function, it creates the length, but while also keeping the string, returns it back together with the length. So we can decouple them again and reuse. And yeah,
nothing gets copied, right?
Yeah,
here.
there's
so
no
that's
copy
an
here.
efficient solution. Yeah.
But this is a bit cumbersome. So, well, we just want to look at the length of the string. We don't want to take it all. So actually, Rust allows us to take not the whole data, but just a reference to it. As you saw from the not recent demo at the beginning. And also quick thing, when we get a more complex type like this pair, we can actually decompose it in place like many languages can, and just do len dash comma is here, and decompose them both from the return type.
Yeah, that's cool, right?
Cool.
Having built-in support for tuples, I would say.
It looks a bit like Go modulo the parentheses.
Parentheses.
Yeah. But this actually is a special type. You can create your own values with it. It is not only used for returning from functions.
Yeah.
Cool. So how do we do these so-called functions? References. As you might have seen in the beginning, we do those using ampersand, right?
Yeah.
Yeah. So let's return this to be just precise. So if we put an ampersand in front of a type, this now means that instead of meaning a whole instance of that type, we only want some way to look what is there. We know that somebody has this data somewhere. We don't want to get the whole of it. We don't want to take ownership. We only want to borrow it for a moment.
Drum rolls.
Drum roll, yeah, buzzworthy. So the same way we declare that we want to take a reference to a string here, the same way is to create a reference. We take a string that we already have, and we just put the same syntax, an ampersand in front of it, which creates a reference to the same string. And let's return this to be just len. And now, suddenly everything works. No cloning, no passing around 100 strings. it works.
So that's what we wanted to achieve, like to keep it simple.
And again, zero copying.
Exactly.
So let's say we'd like to do another thing. Again, if we'd like to do a bit more than just looking at the data, we can do a mutable reference to something.
If we want to modify it.
So let's see what I've written here. Okay, let's just copy this one for a bit. So let's say that we create a function. Okay, this is just the printing. Let's try to call this append name on our reference to a string. And this will be a bit cumbersome, but it's a contrite example. Let's append test. So here, just like we've seen before, if we let this be just a simple reference like it was just now, this type checks, we pass the correct type, a reference to a string, but now the push str method actually wants to modify what is underneath it, and it wants its data to be mutable. But we've said that our data, or the handle to it, is, well, here we've not said it to be, we haven't told it to be read-only, but just like variables, by default, it is constant or read-only. So with the same syntax, if we want to create, to enforce mutability or to allow mutability here, we need to say that we want a reference mutating one to a string. And the same way we created a reference in instance of that type from our small string, we can do the same using the same syntax here. And now it still doesn't work. But why? Because S, as we see, is just a let. And we have something that is by default constant, but also would like to create a mutable handle that can modify it.
Yeah.
But that wouldn't work because we have to also say that S should be mutable as well. And now we can do both the things and get a combined string. Yeah. And here's a really small detail that you don't see in other languages that have references like C++ or Java even. Like in Java, everything's implicit, but yeah, when we declare that something should be a reference, we say it in the type of the argument. But in most languages, when we actually give the argument itself, we would just pass here as the string, and it would magically be either a copy or a reference, like pointer in most cases. So when we call a function, we have to look at the type signature specifically to see what the thing will do with our argument. And when we pass it, we just pass the argument itself without any modification. So if the caller wants a pointer to us, we just pass us. If the caller wants a copy of us, we just pass us again. And we don't see what happens in the back at the call site. But here, everything is mirrored at the callee site. Yeah, at the callee site, we, just like in other languages, we declare that we want something to be either just the data, like taking ownership, or a immutable or a mutable borrow, as we see. And we mirror that when passing. So if we, for some reason, cannot create a mutable reference, it won't try to do one automatically, like in other languages. And you can clearly see when you skim over a file where mutation happens on your data. So you can skip unnecessary mutation, like in terms of bugs. So a bit more on the semantics of read-only and non-read-only references. So We say that at any point of time or at any line of code, at any scope, let's say, you can either, for a given value that you own, like S here, you can either have multiple readers or non-mutable references, just an ampersand, or just one writer or a mutable reference. And this is because, let's say you have a multi-thread application concurrency, woohoo, and you create a mutable reference and an immutable reference at the same time and pass them to two threads that each, let's say, sleep a bit and then do something to the data. The mutable one can write something and the non-mutable one can read it at most. And now we have a data race. So we don't know the read, if the read will happen before or after the write from the mutable reference. And if we only allow writes and reads to be done using those references, if we restrict how those references are created by construction, we actually just remove data races as a problem automatically.
Yeah.
So the same thing for multiple writers, again, data races. They won't be racing who writes to the data first, so that after both writes, it is not deterministic what the value will be. And we can demonstrate that this is the case by creating and storing the mutable reference to our string here manually. So let's say we have a reference and try to do append name using it, and everything is cool. This works. And if we move the, this should work. If we move this below, we should be able to run the main. And now we have test and the bit appended at the end. But now, if we try, for some reason, to create another mutable reference and use it too, now the Rust so-called borrow checker that checks that all these rules that we're talking about apply and are strictly followed.
Yep.
Checks this and starts screaming, wait. You have a mutable borrow here and you use it here. And inside this scope, while the so-called lifetime of ref1 is
ref1 is still alive.
Yeah.
Within its lifetime, we're trying to create a second mutable reference.
While it's in use, which means after its creation and before its last usage, in this scope, we cannot create another mutable reference. So just in the middle here, we are trying to do just that. Then the Rust again stops us that we cannot borrow as mutable more than once at a time, and that this is a second borrow. So this is to show that we can have just one writer. And the other thing is if we try, len is above. Okay, let's redefine it just for the demo. So here we have the opposite scenario when we have a mutable reference in scope again here. And in the middle, we try to create, using the syntax for references, to create an immutable one. And now, Rust again is complaining that we cannot so creating a reference is called borrowing. This is the act of doing a borrow. So we cannot create a reference /borrow as immutable, see no mute here, because it is also borrowed as mutable. So we cannot have coexisting mutable and immutable references. But nothing can stop me from creating many of the read-only ones, but we won't show that because it's mostly...
Yeah, if you ain't going to change something, you can read how many times you want.
Yeah. It's harder to show that we can have many. Okay. So that's that. And a small quick note on
just before the break.
Last thing, a note about lifetimes. So let's say we have a reference to a number, and let's make this a reference as the value that holds as its value a reference to something else, mutable, so we can change to what thing it points to, like a pointer. Yeah. So if we create a variable x and create a handle that would point to some number, we can take a reference to x and create a subscope in which we create another integer, and we try to modify the reference to now point to y instead of x, and then dereference is using the C syntax, whomever has seen it. Yeah. And now this actually doesn't work because, as you can see, the liveliness and such, the buzzwords are coming back again. Y does not link long enough because actually this scope, as it should be semi-obvious, this scope only has the things inside of it be inside of it. Whatever happens in Vegas stays in Vegas, right? Yeah. Cool. So this variable y, as we said, might automatic memory management. Rust automatically creates space for this variable here and removes it here. And here we can see the Rust has told us the same thing. The terminology for forgetting about something or freeing it is drop here. So the value y is dropped at the end of its defining scope, but we cannot have a reference to it live longer than it itself. So that's another part of the type safety, that when we have a reference to some data, we can be sure, because the type system checks it, that this data will not go out of scope and die.
Yeah. So this won't compile.
Yeah, this does not compile, as you see. This is a big red flag. And if we actually delete the surrounding brackets, everything now works again, because actually y, its surrounding scope is now up to here, and this print is in scope, so everything works. But inside this, no.
Yeah, and the compiler deduces all of that for us, so we don't have to manually think about it, which is cool.
But let's say, okay, but what's so bad about referencing y? It's just 8, look at it. Well, let's see the almost same thing, but written in C without the errors. These are other errors because of my ID. So let us create a function that creates a variable a, like before, that is 5, and returns a reference to it. So here it's not a reference, it's a so-called pointer. We use star instead of ampersand. So let us call this function and store the variable. And just so we happen to call another function, that's called disturb, that just creates a variable and nothing else. So what happens here? We take a pointer to something that we know is 5. We do something that shouldn't affect us in any way, and then do a print of the number. So any guesses what this will print? Oops. Source dangling. So we would expect this to print 5, but actually it prints 6, because under the hood, technical detail, this 5 is put on the stack and we get a pointer to it, but the stack for this function is destroyed, and we call another function. It reuses the same space in memory, the same stack, and this is put there. And actually, this disturbs our pointers. So this is what Rust prevents us to do. And to anyone that says that this isn't real, it is real. I can regenerate the binary. We're now in the folder, pardon. So yeah, it's tier 6. And as we can see, we actually get a compiler warning, not an error, a warning, that we do stuff that we shouldn't do.
Yeah, yet again, this is a contrived example. Nobody would do that so obviously, but it happens in larger scale projects as we know the pain in C. Like that was what we were talking about at the beginning. Manual memory management leads to a lot of similar problems.
Yep.
Yeah.
So that was the demo about memory related stuff. So
Yeah.
let's get
I'll
back.
say we do the break about now.
And then continue with
with the next demonstrations. So 10-minute break starts now. Feel free to ask anything if you have any questions, of course, at any time. And,
we're here, we'll answer.
Yeah, we will be here. And see you in 10 minutes. So, welcome back. We have done our little ritual prayer to the demo gods in the break, so we hope it will run even better.
We forgot about
starting from now. Yeah, so we have received a question incoming from our Discord channel, I think. Nice workshop. What is the amount of Rust that is going to be covered? Macros, C interop, or just the basics? We had a slide about that, and I'm going to show it again right here at the beginning. That's our demo plan. And exactly those more niche and interesting topics mentioned here, macros, C interop, we are not going to explicitly cover in a demonstration. But yeah, we are going to mention them explicitly in the things we left out. So you can check in again with our demo plan. We are going to basically stop with our most advanced demonstration here about the type system and error handling. Yeah.
Yes, so we're a bit constrained by time, so this is just one workshop. If we had, let's say, a whole week to delve a bit more deeply into those topics, we would have covered them. But having a one-shot introduction to Rust basics, as it's called, we will cover just the basics.
Yeah, exactly. So I hope that answered the question.
Yeah.
So this is where we were. And now incoming into our next demo part, we're going to talk about composite data types, i.e. defining our own data types. Now, this is our brief bullet point plan, the keywords, key takeaways from this demo. First, we're going to see how we can actually define the data types, okay? 2 keywords are the main participants here, structs and enums. Now, a struct is, I hope, a familiar concept for most of you. We can also call it a record type, and you can think of it like a class, but without the methods. So simply a name and fields with types. That's a simple data definition. And the other keyword we have is an enum, which is also a relatively popular concept, I hope, which is like a type with a finite listed at compile time habitants, right? Variants, we can call them, okay? But you can think of those in Rust like C-like enums, named constants, like named variants, but with a lot of more functionality.
We'll see more in the demo. Yeah.
Exactly. Yeah, that's the demo plan. So then we're going to see the so-called impl blocks, and this is our way of defining behavior on our data. Then next up, we're going to see also pattern matching. Oh yeah, and impl blocks, that's the part that we called methods in the beginning, yeah? We're going to see what methods feel like in Rust. And pattern matching is a feature of Rust, and this is basically the way to actually consume the constructed structs and enums, like actually kind of deconstruct them, see what's inside them, how they behave, which is also a cool feature supported by Rust. And then we're going to just tackle on the surface like a bit into traits and generics. And those are the more like, I would say, abstract and complex OOP notions. And those are the mechanisms of abstracting, generalizing, and sharing behavior across types. So that's our plan, and we're going to jump right into it.
Yes, it's time for the next demo. Cool. So a bit of ahead of ourselves. Cool. So let's start with what simple enums and structs look like. So here I've defined 2 simple data types. An enumeration of that signifies a day of the week. Here we can see that we have 7 variants. We can think of those as separate constructors or like David said, inhabitants of the day of week type. We just know that if we have an instance of something that is of type day of week, it has to be one of these 7 things. Just like if we have a bool, we know that it's either true or false, no, nothing else. And the same, but not the same, we have structures, which again, like arguments, like variables, have absolutely the same syntax for declaring names with types. So name, colon, type, and comma to separate those. We can also create the so-called more like anonymous structs that are a bit like tuples, but have a name associated with them, and automatically create a structure which has field names 0, 1 instead of actual explicit names like person here.
Yeah.
So let's dive in a little bit deeper. And now straying away from C-like data structures, enumerations in Rust can actually, each variant can contain data. It's not just a keyword. Like enums in C are actually numbers behind the scenes, but here each other variant, not only it has a, let's say, an underlying number, or in order which one of the constructors it is, but also can hold data. And the data it can hold is actually the same as a struct. So we can either have curly braces with small mini fields inside with types, or parentheses with unnamed types inside, which again are decoupled like a tuple. Cool. And let's do the same.
That was one example of an enum with more data, like a color.
Yeah, again, it's really contrived for the example to show all the functionality that there is. So yeah, let's make another shape. We'll see what this is later. So let's say we have a shape that is either a circle or with a side that's a byte, or a square that has a side of which is a byte, or a circle which has a radius that is a simple single precision floating point number, or a rectangle variant that has, let's say, its width and height as named fields. Cool. Let's now create or the impulse first. Let's do the impulse first.
Yeah, let's do the impulse first.
Now
this is the part when we simply define data. Okay, as we said, those two things are decoupled, and those are the two ways you can define data. Those compose, and you can scale them infinitely, which is all you need. Actually, it turns out.
Yeah.
In terms of defining data.
These are the two types: structs and enums.
Yeah.
Cool.
Yeah.
So if we want to attach some functionality to our data, as you see, this is just data, we can use the so-called impl blocks, which inside of them, you can see, we can just define normal functions with one small difference, that we can use the self keyword, which automatically refers to an argument of the type we are implementing functionality for. Here it's shape. So this is the same as doing something of the type, but the reference is on the right. It's like doing this, or actually this, or a super shorthand syntax, this.
Yeah, syntax, sure.
So what this function does is we declare a function that is namespace under the shape type. So each type has its own pseudo namespace of functionality that can only be accessed through it. So we create a function in that pseudo namespace that takes as its first argument a reference to a shape and returns a type of a string. And here, as we've said before, because this is an enumeration, here we can see the type of self is a reference to a shape, we can do a so-called match statement on it. So what does match do? It's like a switch statement, but it's an expression. So we can take something that has many variants. Let's say like bool can be true or false. A number can be 1, 2, 3 or something else. We can take a shape and do some logic for each of the cases. So a shape can either be a square or circle or a rectangle. And for each of those, here's a fat arrow with some terminal fonts magic. This is just an equals followed by a right-hand
Angle
bracket, yes.
Yeah.
And then some value. Instead of this value, we can have a whole block that does more stuff like printing. Oops. Like this. And this again is an expression that returns this thing because it has no semicolon after it. Cool. So this is a function that takes somehow a reference of a shape and returns us a string that describes the name of the shape as a string, so we can print it out. And here is another function, this time called area, that also takes a reference to self, or to shape, and returns a floating point number. And this calculates the size or the area of our shape in 2 dimensions. So as we know, a square, we just square the side. So we multiply it by itself, and because we don't need to return a byte, but instead a floating point number, the cast here, as we said before, strongly typed, it is explicit. So we explicitly say, using this postfix notation, as F32. In other languages, you will see this as F32 in parentheses and then some expression like this. Like in C, JavaScript, and Java and so on.
Yeah.
Here we do it postfix just because it's syntax. Don't get
too picky about that.
Yeah. For the circle, almost the same thing. Here we see a bit about the standard library. There is an F32 module, whatever that is, with a const module inside of it that has a big constant pi that is a float that we can use to calculate the area times radius squared. And for the rectangle, it's the same as the square, but instead of a side, we have 2 sides. And to show the other way around to do the casting, we can either cast to float after multiplying, or we can cast both of the sides to a float and then multiply them. And here we can actually see that match distributes actually the reference down. So we have a reference to a shape, but when we pattern match down, we actually see that we come down to a reference to the data inside. So instead of having a reference to the big thing, we can destructure it and get the references of the small things. So actually multiplication is implemented for references to numbers in the standard library. It's not some magic. But casting is not. So we cannot cast a reference to a byte directly to a float. So we have to dereference it first. And how this works is using the star operator as we
actually saw that, but we didn't mention it explicitly.
Yes.
So yeah, consider that a place we mentioned that officially.
It's the same as C, as we saw in the C example before the break.
Exactly.
So yeah, a bit more syntax, but just to show, again, contract examples. That's what we can do just for one workshop.
Yeah.
Cool.
And I don't know if you mentioned what's that with the 2 points above in the name function. Yeah, you have the syntax of the double points in order to... Yeah. You could.
So yeah, the fields or the variants of the type are actually not public. by default. You cannot refer to them directly. And just as I've said that we have a pseudo namespace in which we define these functions, actually that's the same namespace in which we have the constructors themselves or the variants. And we access this namespace by using shape colon. So actually, if we do shape colon here, we also see the name and area methods alongside the three, as we see, unknown members.
Cool.
And now let's combine them to get a color shape that has a color and a shape, and do some combined work on it. So a simple function, let's make a describe function that prints info about the color shape. So we can get again by reference an instance of our type. And now we can use dot syntax. We haven't seen this yet.
To access fields.
To access our named fields. If it were a tuple, we've seen it with a tuple. If it was a tuple or a tuple struct or just normal struct like here, we use the names of the fields and just can access them like this. And again, this is automatically a reference because this is a reference. Cool, so we can create a print with 3 holes for things, the color, and now we can, when we take out the shape, which is a shape, we can directly using dot syntax, like a method call syntax, call the name function. But now you see name above took an argument self. Where is it here? Well, actually, this thing is syntax sugar for was it shape? Yes. Going into the shape namespace, taking the name function and passing self as an argument.
I think it should be self shape.
Self shape, yes, yeah. You're correct. Shape and the reference to that, yes.
Yeah. You can see how the compiler just figures it out for us. Yeah.
So let's undo a bit.
You just can't do it wrong. You cannot do it wrong.
And I think there's a code action for this too. Add reference. Everything can be done automatically. The code action is the little light bulb you see in your IDE on the left.
Yeah.
So this is the same as
what we had previously.
This, yes, syntax sugar. Cool. So this little method, or as we saw, is just a function that has some extra syntax for calling on method on objects themselves with dot. We will describe our thing, and let's see how we use it to construct an instance of our record type or struct. We say the name of the type, open curly braces, and just like above with the types, but instead with values here, we put each member here and put a value for it. And again, just like we destructured above the color and the shape, we can create them using these variants, which are again scoped under the types themselves. So we can use the shape rectangle type or a constructor which takes 2 U8s or bytes, and the same for grayscale. And if we don't like that, we can, let's say, do a square with a height of 15. And here we see the same syntax, curly braces instead of normal ones, and name colon value. Cool. So what does this do? It should just print a string. Cool. This is this type of color square, and now you see this square is the return value from the name method, and the area is the return value from the area method. Cool. If everything is understood, yes. We'll now try to do something more interesting. Let's add a new type of shape. How would we do that? So we know that everything that mentions shapes should start with the definition itself. So let's add a point.
Just because it's funny.
Yeah.
What can you say about a point is just a point. So it has no fields.
So yeah, it's the secret third type of structs that just have nothing. No curly braces, no parentheses, just nothing. It's like a struct with no fields. So let's create a point variant of our shape, and now suddenly everything starts complaining again, because if this were a mere switch statement, it would just fall through all cases and not much on point, because there is no point match arm, and call it a day. But because we have a match expression here, we want to go through all the cases and be sure at compile time using the type system that we always have a value at the end. So Rust is that we have 4 ways to get a shape, but we only handle and give a value for 3 of them. So it is complaining that we have a missing match arm for the point. And this is actually the missing one. We can implement it like this. Again, nothing here because it has no fields whatsoever. And the same for the area method. And now, if everything works, this now compiles, this compiles, we should be able to put for the shape our point like this. Let's see if this works. Yep, this is a grayscale 1, 2, 3 point and has an area of 0. Drum roll. Okay, let's look back what we had to do. So we had the just data thing, and then we implemented some functionality for it. This might as well be just a separate function, top level, which takes an argument of type reference to shape. But as we see below, we've grown accustomed to this syntax from most of the languages we've used, so we'd like to use this more. The method call syntax, I mean. So we create 2 methods, and now we have to modify all of the methods that work on self, because self is now a bigger thing than it was before, and it has to handle more cases. So if we had these implements, as you see, they're decoupled from the data itself, so they can live in other places, other modules, or other libraries. If we package this shape thing into a library and publish it, someone else can download it and implement even more data on it. We can implement data on shapes that we didn't define ourselves to. Like for example, we can implement a method on U8 that just prints something, hello. And now, wherever we are, we can just create a let how n, which is U8, be 5. And now suddenly we can do n dot how, right? It should take a self, pardon. Oh, we can for built-in types. It has to be a bigger, pardon. For string, what we need the example with?
I'd say it doesn't really matter. The cool point is you have some things that other languages take like a more complex approach to. Like in C#, those are called extension methods. You have that decoupling built in here in Rust. You can implement your behavior for foreign types, and you can implement foreign traits for your types. Okay, so that comes built in with within that decoupling as an idea.
The built-in types are a bit of a special case, as we've seen, so I won't be able to demo this very, very well. So yeah, if somebody else uses our thing, they can import for themselves. Cool. So to reiterate again, if we want to add another constructor or like another variant of our shape data, we have to go in all of the impos and modify the functionality that depends on the variant we are in. And as we know, if this impo is not in our hands and in somebody else's code, we can do nothing about it. So if we just push an update to our crate or library with this breaking change that adds a new variant, everyone's code would just stop compiling because they would have to manage this change themselves. And that's sometimes wanted behavior, but not most of the times. So let's look at what we can do to make this more easily accessible. Cool. So looking at this, everything is the same for now. Okay. Here we have almost the same structure, but we swapped two things around. We will now see what. So the color is absolutely the same thing as before. But now, instead of saying that a shape has only n constructors, and then define the functionality elsewhere that can be extended by everyone, we turn the table again and say that the shape is something that has this functionality, but we don't tell what the variants are. So other people cannot touch the functionality, but can make other instances and other constructors. And before we could create other functionality, but no new constructors. So how do we do that? We create the so-called shape, which is our variation of the interface thing from other languages.
Right? I think traits are a fairly common feature in, I would say, not like too many languages, but like they're a popular feature. I would reckon people are relatively familiar with the notion of traits, this is again not the traditional trait you usually see in other languages. I cannot think of any concrete examples right now. Perhaps PHP, the last I heard of, had some traits, but those are different, so we're going to explore them. But just it's not that different from what you might have heard as a trait.
So think of it as a glorified interface, nothing more, nothing less.
Yeah.
But again, as we saw, the just data is just data, so there is no I define a class or something that extends or implements some methods or interfaces or extends other classes. So as we'll see in a moment, implementing the interface or the trait is also decoupled from the data. So now, instead of having the three data types hard-coded, we can just define them as top-level structures.
Yeah, and they have nothing to do with each other.
Yeah,
for now.
Yeah, they're not associated in any way. They're just free structures. Cool. Modular spoiler here. We can now, instead of defining the two functions using the info block, let's do a split here. I think it will be beneficial. Instead of doing an implementation on the shape and create the two methods that just match on whatever the constructor here is, we do the opposite. We define what these two methods do for each of the types instead of saying what the types do for each of the methods. Again, a bit reversed. So here we see the special syntax. Again, it's simple, but now shape is not a structure. Shape is now a trait. So we say that we want to say to the compiler that squares are shapes.
Yeah.
So we say that in other languages you would say class square implements shape, but here, the other way around, we say that square is some data and then say we implement the shape functionality for squares. And how do we do that? Using just the same syntax as here. But now we know that self is not a shape. Self is now a square. So you can think of it like this is not here, so we just implement things for square, and you see this works. But when we say that this implementation block is connected to this trait, this allows us to do other functions. And this allows us to miss functions, not all trait items are implemented.
Yeah.
Cool. So it is almost the same, but forces us to implement specific methods with specific names, specific parameters, specific types, like here. Cool. So we do the same thing for our free types, like before, absolutely the same. And now, drum roll, we get generics, because how would we recreate our core shape? Before we had a shape, because this was the predefined data that wouldn't change, only the functionalities will change. We don't care about those, because the data is just data. It's there, we know how big it is and stuff like that. But if we now want to have a core shape that has any shape inside of it, we now have to be more open about what a shape is, because now, with shape being a trait and it being exposed to other people could create their own structures, which are shapes. So we want to support those as well. So what we do is make this structure generic. So the syntax is just like other languages with generics, let's say Java. We use angle brackets again. But now there's a bit more to it. We can do clauses that restrict what these types can be. So we say, okay, we take a type, we call it S, but if we give me a test, it should, so we read it, be of type shape, but actually this means that this type implements somewhere the shape trait. And the body of the structure is absolutely the same. But now, instead of a shape, we refer to something that we know has the functionality of a shape. Cool. It's a bit tedious.
Function.
Yeah, we will now do that. It's quite a lot of syntax for what a simple thing it does. And you get used to it, but yeah,
it's a trade-off. It's a trade-off.
Yeah.
If you want power, you gotta sacrifice verbosity in this case.
Yeah, so if we try to do the implementation again, we see it's again just an import block. But now, if we talk about the core shape, we can't talk about it generally. We need to talk about it specified, or what's the term?
Concrete, yeah. We should
concretize
it? I don't know.
Yeah.
Specified.
When we know what S is. So if we don't know what S is, we can actually say, okay, I'm doing implementation for whatever S is, again, given it is a shape, and implementing for that S methods on core shape with that S. Cool. So let's say if we try to call this a method that is defined for core shape of S, Rust will check if this S is S of shape, and if it is, then this import block would be usable by us. If we create a core shape of some other type, if we could, this could be gone, it wouldn't work then. So yeah, with a bit more syntax, just like before, we can define absolutely the same function, and we can just call .shape again with .area. But now, knowing that the shape argument is just of some S type, which is implementing the shape trait, we know nothing more about that type aside from the fact that it is a shape, which means that if we do a dot on it, we can only do name and area and other methods from default traits that are implemented on every type, but we won't go
there.
Yeah. So yeah, we can't access the data of the shape. We don't know what it is. We can only call the methods that we have signed a contract that it should have.
That we will implement.
Cool.
Yeah, exactly. Is that a polymorphism thing? I mean,
this is exactly polymorphism.
Yes, that's how we achieve polymorphism. Yeah.
So instead of interfaces and directly taking a type, an argument of the type of the interface, we actually say it's one step longer. We say that we take something of a type which implements the trait slash interface.
Yeah.
And back to the main, it's exactly the same. We see some folded lines here. We will see why in a second. So this should run absolutely the same. I think. Approaching which. So yeah, same thing. Rectangle area 40. And now let's go back to how do we define a new shape. Before, as we said, we had to go to change the enumeration and then go through the impose. But now we see that each of the instances, each of the variants of this shape, now it's not the mathematical term, it's not a closed set of things, it's now an open set. Everybody can put new things in it. So actually, Rust allows us to define structures and even implementations inside other functions just because sometimes we want to have some local data. So here we can define a struct point. Again, nothing here, just like before, but now it's a top, actually not a top level, but just a struct, not a variant. Yes.
Yeah, we did this to explicitly illustrate that you can do that anywhere you want.
Yeah.
It's completely decoupled as long as you implement the shape interface for it, right? The shape trait.
So yeah, even inside the functions, we can create this. We can do the tiny bit of change that we had to do here, which is to tell what point does for name and what point does for area. If we, like I said, do the reversal, we have to do them in one place instead of doing all of the types for each function in one place. So using this, we can actually have a shape point now.
Yeah.
Without changing anything above this line, because everything from here to the top is already made generic enough that we can insert our own data here. And let's see if this works. It should us. There aren't any errors. Yep, point with area 0.0. And just for demonstration purposes, if we didn't have the info here, now we see that we make a core shape where a shape is a point. The point still exists. And Rust tries to guess what the type would be. It would be a core shape of a point if a point was a shape. But now we don't satisfy a trait bound, or the so-called trait bound, which is this, that S should be a shape. And again, the errors are spread out everywhere and annotated to all the associated things that are involved in the error. So here the struct, the trait bound that is not met, and the point of failure where the problem occurs.
Yeah, I hope you got convinced thus far that we do really have a smart compiler for Rust, right?
Yeah, and even if we could construct a core shape with point, that means if we didn't do this trait bound, and we just said that a core shape is something whatever and a color, but implement the describe functions only when that whatever is a shape, then we could create the shape and it would be a core shape of a point. But now the describe method wouldn't be visible for us because the S we are working with is a point. And the error here would tell us exactly that there is a method describe for this struct. But again, the trait bounds are not satisfied.
Yeah. We could say that's another keyword, trait bounds. You see that a lot in errors.
Yeah. And again, if we do the info, everything works again. Cool. So that was the small demo for the enums, structs, and traits and how they work with each other, right?
Yeah, and now that I think about it, when talking OOP, like solid principles, you all know them, I hope. Ain't that the O in solid? Like open for extension, closed for modification? Yeah, cool, I hadn't thought about that. So yeah, we are OOP, arguably, with Rust.
Yeah, here's the OOP. We can either do this or this, whatever is better suited for the problem space.
Exactly.
Cool. So
yeah, so that was demo time number 2, and before our last demo, we're going to talk about a little bit about type safety, right? And that's the topic of our last demo, as we saw in the plan. So we mentioned type safety is a really cool and core feature of Rust, but okay, we also clarified that we mean by that a static and strongly typed language, right? And that's fine. I would say that's graspable in technical terms, but why would we need that? Okay, what's cool about that? And we are going to take a look at this question through the perspective of error handling. Now, if we weren't so online and so decoupled, I would ask you interactively here, let's think together about ways to handle errors, like generally in languages, your language of choice. And yeah, I won't wait for answers right now, but generally, I would say 2 things spring into my mind, right? One very familiar concept is the null keyword. Like if something goes wrong, I couldn't produce a value or something, or I simply want to say something is invalid, I simply return null, right? And we are all fairly comfortable with that notion. We're all used to doing null checks or null pointer checks in C or C++.
Or Java.
Or Java, yeah, Java.
Or Go.
Or Go. Or a lot of languages, yeah. So that's a thing we can do. And another thing we can do is throwing in catching exceptions. You know, like specifically in Java, I would say that's a really established mechanism of avoiding control flows, a bit under the rug. Yeah, throwing an exception somewhere and then hoping someone will catch it and handle it anywhere else.
Hopefully.
Yeah, and pure developer contract. And some people are pro like checked exceptions. Some people say they suck. Yeah, it's a debate. But that's a thing a language can do. Well, we'll stop here, and I'm gonna tell you that Rust does neither of those, and instead we have types. Okay? So all of those issues go into our type system. So what we got here? Instead of null, we have an option, which is a generic type parameterized by a single type t, and a result with 2 generic types t and e. Now you can probably see the semantic analog between the two. An option is simply, now bear in mind, those things are no complex things, and we're actually going to see their implementations right here, so we can talk a bit more hands-on.
Here's
right?
Everything, nothing more.
Exactly, that's everything you need to know about those 2 types. And you can see how option is analogous to null, right? But it's rather an enum with exactly 2 variants. You can either have nothing, which is a label, one exact label for nothing, or you can have something, which is a constructor in which we pass a value we have, right? So get used to that idea if you want to do Rust. And similarly with exceptions, instead of catching an exception somewhere else and handling it then later anywhere else, we simply return that exceptional case as a value. And errors as values is a concept we can kind of mention here. Yeah, there is this idea called errors as values. And yeah, that's what result does. It has 2 types. We either succeeded and produced a value of type t, which is this constructor here, okay, or we failed, but our failure is encoded in a value of type e, okay, and you're free to define those however you wish, whatever makes sense for your domain. Okay, so this is what Rust bets on. We don't have any nulls, we don't have any catchable exceptions. And coming to that, well, you might say those 2 types, they make things more explicit, but also more cumbersome, more difficult to work with. But don't worry, we are going to see the magical question mark operator, which eases a lot of that verbosity. And we're also going to get a feeling about why we call Rust a functional language, like really as an experience in our following demo. And with that, I think we're good to jump into it. And we'll, I think, try to keep it briefer.
Time for the final demo. Cool. So, firstly, let's see a small bit of code. We have a main function, and we have inside of that function, so we create another one, which returns a byte, and we use that actually this type, like the shape we had in the previous demo, is actually a pseudo namespace and has things inside of it, including some useful constants like max, which is here 255. Instead of typing out, we have a lot of small, how do you say it, helpers like this to alleviate common conundrums close to handling numbers and such. The same reason we have pi. Cool. So let's say we have the maximum number we could have, and assign it to a value, but add 0 to it. What would that result into? Well, nothing. That would be just 255. But if we decide to add something more than 0 to the maximum value of a byte, what should happen? Well, some people would say that they should just overflow and return 5. Some people that say that this should be a saturating addition and just leave it at 255. And there's Rust that rushed out that actually adding with overflow is well defined, and the definition is it doesn't work. So cool. We have something like exception here. It's called a panic. As you see, it's a so-called end of world scenario, and something panics. It's like aborting the whole program, everything.
Yeah. Your program dies. That's an end of world scenario. Non-catchable exception. You can think of it as.
So we don't like this, but it's good for a default. Like we expect adding two numbers to just work most of the time, and when it doesn't, cool, it doesn't. But Rust actually allows us to do more stuff. Oops. Oh, we had that in the demo here already. So yeah, it happens. Cool. So we saw that this actually exploded, but aside from literals and summing, there is actually a plethora of functionality that is imposed for simple number types. So you see on the result of the max function call, we know that we have a byte, but we can call methods on that number. We can do it on the literals too, which looks kind of cursed sometimes, but yeah. So if we do check that with 50 instead of just adding 50, we now don't get a byte. We get an option of a byte. So what would happen if we run this now? Finished process with 0, but now the value is, drum roll again, none, which is one of the two constructors for option. And what would happen instead if we added 0 but checked so that the errors are caught? Now we'll get something. Here it is. Here is a 255 in a simple so-called tuple struct with one field. Well, how do I know which one of those we have without running the program and seeing the output? Well, as we saw in the last example, you can just do a simple match. If we do, there is actually some snippet matching that the language server does. We can match on a value and automatically create arms for all the constructors. So here, let's say we have n. Let's name the field n, and the body. Let it print. We got a value. Here it is, and here we did not get a value. Here it isn't.
Buttons.
Cool. And now, if we run this again, oops. Here we got a value, 255. And if we do the other thing, hide this macro. And now we didn't get a value, here it isn't. Cool, so this allows us to, so again, a contrived example, you wouldn't use something like check that if you are not doing some embedded stuff, or maybe some hardcore blockchain proving.
By twiddling.
Yeah.
Yeah, but the cool thing is you have that in the standard library, in the language encourages to write code like that.
So you see that,
which is why it's safe.
Yeah. Even though result and option are such simple types, as we saw, they're just two variant enums, both of them. Their use is encouraged mainly by having them exposed by the standard library and appearing everywhere where something might go wrong instead of panicking. So let's look at an example for how result looks. Let's say we have a string 1 through 3 and we want to parse it. Well, there is actually a parse method which comes from a trade that we won't go into, but actually this parse method can parse a string into anything. And here we say that we want to get a U32. So parse magically knows what that means. It infers that we want a U32, selects the correct implementation. And we don't say what the error is because parse actually defines that the result is something that it knows what it is, so we don't need to specify it here.
Yeah, that's a placeholder for I want you to figure that out, infer that.
It's called a type how, and it's filled if it can automatically. If it can't, it will say type annotations needed. Cannot see what this is. Cool. So we try to parse the string and we get a result of either a byte or something else. And here we actually, if we do a match again, but now we do an OK and an error instead of some and none. Now both of the cases have data attached to them. The OK case, analogous to the some case has the actual carrier data, but now the error case has the data for the error itself instead of just saying none, like it's the case with checked adding. Now we get an actual error that gives us more data, more info about what went wrong. Think of it as the fields inside the exception that you throw in Java, let's say. So again, we can do just print in both cases. And let's see what happens here. We get a cool number, 1, 2, 3, and it's parsed correctly. But if we change it from 1G3, now it should fail. And now it fails with, and here it is, we can print the error, invalid digit found in string. Not the best error, it could be better, but yeah.
Standard library for it.
Yeah, and you see here, Rust Analyzer, the Rust language server, one part of the amazing tooling that we have, actually tells us what the type is. We don't need to import it, we don't need to say exactly what it is. We know that it's there, we won't refer to it directly, like accessing fields and such. So we can just use the fact that it is printable, which is actually using another trait, and does that. We know that we can pass it to print line, and we don't need to know more. Cool.
Yeah.
And now the hardest example. Let's try to parse a multi-line string containing space-separated numbers which are bytes.
Yeah. Essentially a matrix of bytes, line by line, space separated bytes. We're going to parse them from a string, but you can imagine that's the user input or any source you like. Okay? A string comes to you.
So here I don't actually need to hide this. Let me re-enable the floats again. Cool. So this is a sneak peek into what macros look like. We won't delve into those as we are already a bit over time. Sorry about that. So this derived debug actually creates an automatic implementation of the debug trait for this type, so we don't have to do it ourselves. And this debug trait allows us to print types for debug reasons. And as we can see here we've imported something from the library, and the keyword to import something from somewhere to be available in your scope is the keyword use. And here we can say use everything from the pseudo namespace myError, which is just an enumeration, which has two possible variants. So as we've said, we'll try to parse them, but we'll parse them into U8s, these numbers we have. So we want to differentiate and tell the user more info, that either we will have a parsing error that comes from the parsing itself, as we saw in the last example, or we overfloat because of the
addition I'm trying to do afterwards.
Actually, yeah. Yes, and let's do an addition so we can have more errors. Cool. Yeah. So we won't explain everything line by line that happens here, but looking
across, like roughly,
we can take the input, which is a string. Let's say this comes from the network or whatever. We can get an iterator on the lines, which is a whole other topic, but think of it as magic that lets us do stuff for each of the elements well. It's like a for, but better. If you've used Java, this is just like the Stream API, but it's called iterators here. So we can iterate over the lines, and then flat map, which is like mapping, and then flattening the double nested chain of things that goes inside. So we can take each line and split it by white space, which returns us another iterator of the things separated by white space. So by now we have an iterator from all the things separated by white space and new line. We can map those using the parse method that we saw before, but specifying the generic type here using another special syntax. And by now, as you see,
it gets complicated.
And we see that we now have an iterator that is some result because of the parsing. And as we know, we just parsed, so we know that if we try to map, whatever we have now in the compare is either a cool byte or a parsing error like last time. And we can use some functionality of the result type to convert the error into our error using the parse error constructor, which wraps around the parsing error and gives us our error. So in the bottom case, we have our error. And using more magic and more unwrapping of the inner types, we can also try to add 100 to the inner n. And if it's okay, it's all good. This is a converter from options to results. If not everything is good, we can create an error. And again, we can create an error of our type. So at the end, if we collect it into a vector, which is something like a dynamic array of those results, it can figure out which these types are. We get a big vector of either well parsed bytes or my error. So let's run it for a bit. Yes.
Could we summarize what we're trying to do?
So we get a string we split it by new lines, then we resplit every line by new spaces. We try to parse those things into numbers, and if we manage to parse those, we try to add 100 to them. And if we manage to add 100 to them, everything is fine. If not, we know that either the parsing failed or the adding 100 failed. So if we run this, we'll see the result is an array. As you see the syntax here using square brackets like most languages. And we firstly parsed 1, added 100 to it and got an OK of 101. Then the 200 parsed correctly, but when added with 100 overflows to 55, so we get an overflow oops. 4 works again, and G doesn't parse because we get a parsing error invalid digit.
Yeah.
So
and the cool thing right here that we wanted to showcase is that you have all the explicit information about what went wrong at which step and with which entry in your vector.
And you have to
handle them before you can work with those.
And it can be a little bit overwhelming.
Yeah, but that's by design. So don't worry.
Yeah.
That's the master example for the end, just to entice you to be interested.
Yeah, instead of doing all of this map nonsense here, we can actually just define a function that takes the string that we got here after splitting by white space and returns directly the result of either the byte or my error.
Yeah, that's kind of abstracting the business logic, right?
Yeah.
That's what we want to do. We want to parse the string in
because, as you see, this is really unreadable. So what we can do is just make a small functions. But what happens here? We do sparse and map the error, and magically we get a byte back instead of the result. We get this number, we do a check that, and again the OKR, which creates a result from the option, and again we get a byte back. Why is that? Well, if you squint a little bit, you can see here we have a bit more syntax that we haven't talked about. So this is the question mark operator, which placed after an expression of a result or option type converts into code that checks what this thing is, and if it's the good variant, either sum or OK for respectively option and result, it pulls it out and gives it to you directly. And if it's the bad thing, either none or some error, it automatically tries to return it from the function you're currently in, here parsing at 100. So because this is a result of my error, this question mark operator gets this thing. If it's good, gives us directly the thing inside. If it's not good, lifts its hands and tells us, okay, this is the error, get out of the function. It's like throwing. Short-circuiting return. It's like you can think of it as throwing, but actually you throw a value, not an exception.
Yeah, exactly. It saves you a lot of boilerplate.
It's the same as matching and returning in one of the cases. And as we see, it's a bit more, I'd say, readable instead of these chained maps.
Yes.
Cool. So if we replace those, we should see the same result here. We can just map using this function. And again, functional programming, higher level functions, we can just pass this function as an argument to this method, and it just works. And again, the result should be the same. Yep. And now for the final bit, let's do a little swap around. And instead of saying, okay, collect this whole thing of maybe errored out parsing and adding operations, instead of collecting it into a sequence of small, maybe errored things, we can say collect it into a maybe errored all of the things or the error. And this implicitly converts our data from a list of results into a result of a list. And how is this done? If everything is okay in the list, we get an okay of the actual data inside in a list. But if we have just one error, we drop the whole list and just get this one value as the return from the whole operation. And if we see here, the first error we get the 200 that overflowed, we get a whole error of oops for it. And if we fix it and the G2, or not, let's see the G error link out 2, and now we get the first error that we come to is this one.
Say parser.
And finally, if we also make the G do something good, like 5, we should see an OK of just the good data. No OKs everywhere.
Yeah.
So this was the demo to show you, not in too much detail, how you can use in practice option and more often than not results and your own data types to really explicitly say what can go wrong, how do we manage it going wrong, and so on.
So that's how we write safe and memory efficient code.
So yeah, you would think that this is not really memory efficient, but actually options when they translate to underlying codes and stuff actually get simplified down to optional pointers. So it's either a no pointer with nothing, which is the same as the none, or it's something and it's a non-no pointer. So these things look like a lot of overhead, and if it compiled super simply down to assembly, it would be a big overhead, but actually there's a lot of optimization just for, not only for this, but for these especially types, so that they're performant, but also type safe, and by using the question mark operator sparingly, also really elegant and
convenient.
Convenient, yeah,
Eloquent,
to
you
use.
could say. Yeah.
Cool.
So I'd say that concludes the practical part, and of course, if you have any questions, now would be a good time to ask them. But just to rush it out real quickly, we will try to draw a conclusion. Some things we left out. I must mention things that we didn't simply have time to cover here. Macros. So Rust has a really extended and extensible system and tooling for writing your macros, which is like simply pre-processing compiled of your code. That's code that generates code, and it's written in Rust plus a little special syntax, right?
Don't think about C macros that are just string mushing that hopefully comes out as a valid C code. Here we can actually work on the abstract syntax tree of the code. We take the code as data, like a list of statements and such, that we can do.
Yeah.
It's like working on data, just like we work with these results.
Exactly. But it's a whole big topic, right?
Yeah.
Next up, modules. You see, Rust has, we talked about encapsulation. We have a module system. It's quite good. We didn't go there. We also didn't investigate how cargo.toml works in detail, but that's like a really developed build system. You can do a lot of things, a lot of specification optimizations, dependency management. That's a big topic. We also didn't talk explicitly about developer experience, and by that I mean how you feel writing Rust, right? Now, initially, we wanted to split the demos, so some of them would be made in VS Code by me, and some of them would be made in Vim by Pavel. But yeah, we chose Vim at the end because we wanted to show that you can have that very fluent experience with, customizable, extensible, and Rust provides with a really great tooling in terms of language service, provision, IDEs, plugins, a lot of things. So it's a rich ecosystem.
There is a JetBrains IDE for Rust if you want one.
The Rust rover. And I do it in VS Code. There's a lot of tooling there, and the Rust Analyzer, of course, is the all-in-one plugin that everybody uses in VS Code. And on the more advanced topics, asynchronous Rust, we really wanted to, but we decided that would be too much. But we only mentioned that at the beginning. We couldn't show it. And also a lot of topics we didn't show, but bear those in mind. Yeah, it's a really wide topic,
Indeed.
Rust in general. Yeah. So, all things good, very nice, we were chilling, but it's not all roses and happiness, okay? So, we will mention, like to show self awareness, we'll mention the known drawbacks of Rust and why it can feel cumbersome and not so cool, okay? So, Ferris is a bit sad about that. Yeah? Okay, so first things first, of course, its learning curve is really steep. I would say that's natural because you have more power, but also you want security, right? So you got to trade off. You got to learn a lot of new concepts, all those memory safety mechanisms, all those new types. It becomes cumbersome, it becomes confusing. A lot of places, Rust is opinionated, and you gotta learn how to work with it, right? So that comes at a cost. Yeah.
So if you want us to do things for you, specific things like checking that you don't reuse memory and such, you have to learn how to tell it to do that. And the more you learn how to tell your compiler things, and the more it can understand, the better your code can be. But also the harder it is to start talking to your compiler. And by talking, I mean like writing code, but it's almost like a conversation with Cargo because
It
really
replies.
it replies maybe too often. Yeah.
Yeah, exactly. And yeah, doing all those things, that's how we get to such similar situations, right?
So we've talked about having a couple of string types. We've briefly seen the top two ones, but there's a couple of others. Each have their own use case. And when you do systems programming, mostly it really matters which one you use.
Yeah, and when you try to do asynchronous Rust, there's a lot of buzzwords, like a lot of stuff, a lot of overhead to learn, I would say.
That we didn't
So-
go into.
Yeah, we didn't go into it, but only in things concurrency and thread safety and memory management, you can go insane basically. So yeah, there's a funny meme about that here. Those are some of the experience, the frustrations of Rust, right? So next things next. It's syntax. You might have gathered that it's really verbose, yeah, but that's again part of the trade-off. It's also really strict and restrictive because it won't compile until everything is perfect. Okay, everything type checks adds up and your binary is safe and super cool. It won't compile, so it could be frustrating when you want to change that little thing, or yeah, God forbid, mutate something, make something mutable. Yeah? That's when you get the headaches, right? So yeah, it could be a bit scary, especially at the beginning, especially for not that experienced people, I would say. So yeah, you can compare that with Python, and we can laugh together, right? We can have fun together using that. Yeah, as you might have gathered, that's how you read an integer from the input, and we did a little showcase about parsing numbers, right? And yeah, that's how you do it in Rust. It is verbose, okay? So next things, really popular drawback of Rust: slow compile times, right? We said that Cargo is very heavily tasked with the duty of defining, downloading, compiling all of your dependencies. Now you can imagine how that scales, right? It becomes really slow relatively quickly when your project grows. Because it just takes resources, right? All of that type checking, all of that compile time stuff that's going on, so that you don't have to worry at one time, right? It takes a lot of time. So yeah, that's a situation you can find yourself oftentimes in. Like my code compiles. Like I got 2,500 dependencies they're building for like hour and a half.
A bit of a stretch.
Could
but
be extreme, yeah. But yeah.
There's incremental compilation, so after the first compilation, everything, when you reiterate on the code, it should be faster. But yeah, the first compilations can prove quite long.
Exactly. And of course, a personal favorite of mine, it could become very hard to read at scale. Now, the two biggest culprits, in my opinion, for this are generics and that implicit type inference, I would say. So we only tackle that, but you can imagine in production code, you're trying to understand how a particular piece of code works, right? Or how a particular data flow goes, and you're trying to inspect that, and you it's easy to abuse a lot of generics, and it becomes just really hard to figure out which type is now the concrete specification here, and how that even works, right? So you get to observe things like that trait here, okay? So that's a single type, right? A single interface with a lot of information on the type level, right? Like there's an entire, like half of the business logic goes in here, right? And there are also a lot of cryptic stuff that we didn't discuss. But yeah, that's how it is. And also that, right? You hover on a function and you want to see the type of your argument, and Visual Studio Code says this.
Take this bucket of trade balance.
Go figure, right? It's cool that everything is explicit, nothing goes on behind the scenes, but it becomes a bit tedious.
Also, these are not super concrete examples. We both took those from our own projects that we worked on blockchain-related stuff with Rust.
Yeah, so those are the things to stumble on, right? Just so wild in nature. And yeah, lastly, we mentioned at the beginning how it's a popular, thriving language, but it is not that widely adopted. I mean, not that widely adopted in the sense that it is not comparable to Java or JavaScript, I should say. I mean, it's no industry-wide standard, a go-to language that everybody massively uses yet. Now, yeah, not that many jobs with Rust out there, and we hope we don't get fired for making a joke, right? But hopefully the domain you have come to visit a hackathon on is a main application domain for Rust, so we get to enjoy that in the blockchain sphere, right? And that's cool, and we love that. And before we leave you, we have listed some further resources, real quick through them. The Rust programming language is the first link, that is the Rust book, as we call it.
Yeah, you hear the Rust book referenced all over the internet. So if you hear or see that, they mean this.
Exactly. Rust by Example is a really nice repository with practical examples that you can follow to get a more exhaustive picture of all the things the language is capable of. So it's a nice place to check things, to just learn new things. Of course, the standard library is your go-to search place for all things, standard library. That's the site we have linked. And Crates.io is the official public crate registry. So that's where most of your packages live when you want to use somebody else's code, right? And with all of that being said, we thank you for your attention. And yeah, maybe we should apologize for dragging it out a bit over time. Sorry for that. But that was everything from us. And we thank you again.